So we're given two conditions. First, that f is a convex function, and second, that it's strictly decreasing. To start, we always have to write out what we're given and what we want to prove. So we're given that f is a convex function, which we'll write down the definition for the definition of convexity. And second, that f is strictly decreasing, which means for every p less than or equal to q, we have f of p greater than f of q. What we want to prove is that the inverse of f is convex on f of I, which means that the inverse of f, called f negative 1, is convex on its domain, which is f of I, because it's the inverse. So we can plug in f of x for every place where we have x or y here, and then we get this definition. So this is what we want to prove. This is what we want to somehow get to with what we already have. We can first say that f is convex, right? That's the definition over here. And since f is decreasing, we know that the inverse of f is also decreasing, if it exists. So we can apply this and say that the inverse of the left side is, we flip this sign to be greater than the inverse of the right side. So you cancel the inverse with the function because that's the definition, and then you get tx plus 1 minus ty is greater than or equal to the inverse ff of tf of x plus 1 minus tf of y. Then we just apply this because x equals the inverse of f of x, which is the definition, and y is the inverse of f of y. Well, this should be a y. And this, we can just leave it as is. Because, going back to the definition, we have that this is still the right side of the definition. So this is what we reach our proof.